a pleasure to be here too. Let me accept. So it's a pleasure to be here and give you a bit of an overview of what we do at my group, the Chair of Structural Mechanics and Monitoring at ETH Zurich, which, as mentioned before, is part of the Department of Civil, Environmental and Geomatics Engineering, but we work at the synergy of multiple fields, thanks to our association to the so-called discipline of structural health monitoring. So before I start, I would like to explain a bit on the components of what we call the chain of structural health monitoring, which essentially comprises the following stages. First of all, the aggregation of data through the use of sensors from engineered systems. I will explain that we work with all types of systems, but you can imagine that the sensors can be deployed nowadays from smaller to larger scale systems. We do not work, of course, on the hardware, but we do work on the proper or optimal processing of the signals that are stemming from such acquisition software. And the purpose for gathering these signals is primarily the task of condition assessment, which is often summarized in the subtasks of diagnosis of the current condition of a system and prognosis of the future, let's call it, or remaining life of the system. Now, a particular focus of our group, which is also associated to the name of our chair as Chair of Structural Mechanics, is the fusion of these of the data with models that draw from underlying principles of physics or dynamics, or let's say first principles, as you might have heard this referred to in other contexts, for extracting robust indicators. In fact, indicators that are not only applicable to the individual component or unit level, so a machine or a bridge or a structure alone, but also indicators that can be used for decision support at the level of what we call the population or the fleet, meaning the assembly of these systems. And you can imagine, for example, a wind turbine as a member of a population within a wind farm, or bridges within the roadway network comprising, again, a population of structures that need support for decisions on their optimal management. So this is a bit of the whole chain of where we try to contribute with our tools. And this is a bit of a summary of the domains of our activity, so that I explain, as I mentioned before, that we're not what you would imagine as a traditional civil engineering group, because our activity spans different types of applications. Starting from applications in the domain of transport infrastructure, where we work a lot with what we call mobile sensing, or what is called mobile sensing and onboard monitoring, meaning use of sensors that are deployed on board vehicles for assessment not only of the vehicle condition, but also of the condition of the underlying or traversed infrastructure. We have a group or a subdivision that works on the monitoring of wind energy infrastructures, offshore or onshore. You see a member of our group actually here in one of our deployments in Greece. And this is part of our ERC starting grant that was mentioned earlier, that was particularly on this theme and started, let's say, a whole direction for the group on the domain of energy structures monitoring. We also have activities in the more traditional aspects of civil engineering, for example, seismic monitoring of bridges and buildings, as well as your typical type of monitoring for understanding the behavior of built structures. And of course, we also look into the condition assessment of components that were traditionally the field of structural or condition monitoring was developed, such as, for example, assets, industrial assets, bearings being one such typical example. So in other words, anything that can be considered a structure and which usually could come with a model of each structural mechanics and where we can deploy sensors is for us an interesting or a potential domain of activity. The main focus, and that's also what will be the highlight of, or let's say the main theme of this presentation, is the coupling of these tools with simulation or models. And so I'll try to explain how this can be exploited. But first, I would also like to explain how much we can achieve purely on the basis of data, because this as well should not be overlooked, especially nowadays where it's maybe even a main actually theme. So the very first thing that we can learn from data is essentially what already exists in front of our eyes. And one such source of data is images and videos. And that's something we nowadays exploit as source of information also for structural assessment and condition monitoring of structural systems. Here we show you an example of previous work where we showed how vision-based information, just by using cameras, can give us an understanding of the way in which structures deform, which is indicative of their performance. Of course, a few tools need to be used there to enhance the information that comes from vision, such as magnification and other techniques. But here we do not use much more in terms of physics other than our knowledge, or other than the knowledge that comes from the data itself. And something similar is done in the task of damage assessment, such as the detection of cracks, for example, on bridges or buildings, where again, a main source of information can be purely based on the images that we derive, and automated algorithms that see to the detection of cracks or the understanding of flaws that are typical of structural deterioration. Again, here, tools that are used have to do more with the side of the processing, not necessarily of the physics, but it should not be overlooked that a lot can be achieved purely on the basis of such information. Something similar for us also is achieved in the domain of wind energy monitoring, where we gather data, so-called SCADA information, at the nacelle of the wind turbines. This is something very typically gathered from these systems, where we have information on the mean wind direction, speed, and also power production quantities for each and every one of these turbines in a wind farm, and where we would like to achieve tasks that have to do with the assessment also of the loads that are experienced by these wind turbines, loads that have to do with their fatigue life, for example, that are useful for the engineers in order to understand effects that are interactive effects within the farm. For example, what you see here is the very famous image of the wake phenomenon, where the turbines that are exposed to the wind have a different behavior, or actually exert a shadow effect on the downstream turbines, which in turn also affects the type of loads that are actually experienced by the systems, depending on their configuration on this wind farm. In this case, it is not very easy to develop very precise models of what exactly is the physics that is going on. And so here, we capitalize on data to go where models cannot necessarily take us. To infer the reality of what is going on in this wind farm, we used the conditional variational autoencoder, which gave us a generated model complete with some uncertainty quantification information on what would be the loads experienced by the farm, depending on the mean wind speed and direction on this site. Something similar we try to do with bearings. We try to predict the remaining useful life of bearings on the basis of experiments to failure. Now, the very nice thing about industrial assets that are basically identical is that we can actually reproduce or use experiments on components that are very similar and are expected to behave in more or less a similar way, which allows us or gives us the luxury of trying to use data for extracting models that are predictive of the remaining useful life of these systems under the regular operation. This task in itself is not trivial, and oftentimes we have to deal with data that is not stored appropriately. We have issues with imputation, and here we try to develop a method which receives data that is non-equidistant and tries to achieve the task of remaining useful life, of course with some uncertainty, which grows smaller as we go closer to the actual end of life, so zero life of the system. But again, here we did not use any physics. What gave us the luxury, as I mentioned before, to do this is that we're dealing with components that are identical, and we do have these experiments to failure that are possible thanks to the manufacturers who are actually in the process of certifying these components and are developing these procedures for experimentation. Now, in real life operating systems, actually, we seldom have that luxury. Many of the structures that we deal with are themselves unique, and it's not possible to promise that we can monitor them under very high loads or under very many instances of failure. So here we have to follow a slightly different approach. We try to here exploit some further underlying principles to try to make the most out of the data itself. So I'm going to give you here such an example using a wind energy structure, a wind turbine. And here I'm showing you actually the spectrum of the response. This is the dynamic response of such a turbine, an actual turbine that we have been monitoring in Germany. And you see here the spectrum of the acceleration at the top of the tower. And you see that if we look at the frequency range, we do not have a constant spectrum, which means, or stationary spectrum, which means that we here are dealing with the time varying phenomenon. We have a modulation of the dynamics of this turbine over time. This is a 60-minute interval, and the modulation is due to the dynamics, due to the interaction with the wind. But even if I was to look at a much lengthier time scale, again, I would be able to see a modulation of the dynamics, this modulation in the spectral domain over a period of a month, for example, which is due to slower evolving influencing agents, such as the variation of the mean wind direction and speed on the site, or even the temperature variation, for example. So when monitoring such an operating system, we have to be in a position to account for these effects, which are oftentimes individualized and not necessarily predictable through experimentation. So here's how we do this in this case. We're trying to fuse the knowledge of the dynamics that we know is underlying the phenomenon. First, by gathering response dynamics information from these systems through appropriate sensors, such as accelerometers. We try to develop time series models that are fitting for the phenomenon that we observe. Usually these are time series models, and they have to be time varying for the case of wind energy structures due to the behavior that I showed you before. And secondly, we try to express this dependence on that slower scale, the dependence on the environmental and operational variables using appropriate coefficient models. These are basically dependence models of the dynamics that I observe, conditioned on the temperature variation, the mean wind speed and direction, and so forth. By using such bicomponent models, we have a hierarchical surrogate, as we call it, which though can be used to predict the response of the system. And if we can do something like this, it means that we can also compare this predicted response with the one that we measure, which is a means for us in condition monitoring to create so-called data-driven indicators of the condition of the system. Here is how we typically build such models, these parametric representations of the dynamics. We try to observe or use our knowledge of the system that we're monitoring, which, for example, could be nonlinear if we have behavior that is nonlinear due to material linearity. Non-stationary, as I mentioned before, because the dynamics of the system is changing. Possibly this could be the case of a train traversing a lean bridge, for example, or a time-varying system, which is again a non-stationary system, but also with more particular characteristics in this case, because we have a dependence on the rotation, for instance. And for each and every one of these representations, provided that we know already that the rough nature of the system follows one of these categories, it turns out that we can use an appropriate series of parametric models that can follow this response, and that can additionally be made dependent, because they are parametric models, through their coefficients dependent on the slower influencing agents, the environmental and operational variability. So here, we're not yet using physics, but explicitly, but we did try to fuse some underlying knowledge of the dynamics as a first stage. And here's the first implementation where we have achieved such a task. As I mentioned before, we instrumented the turbine in a location here near Lubenau, or in Lubenau in Germany, and a second one in the University of Bochum, where we extracted such spectra. And the spectra is really the contour plot that you see beneath. And on top of it, you see fitted in the blue lines the predictions of our time-varying model, a time-varying autoregressive type of model that was especially designed and conditioned to follow the dynamics that we observe. Now, the standard approaches would have given you predictions that are usually averaged, something that looks like the dashed lines of this example, and which is really a very rough approximation that oftentimes, at least for our tasks, is not sufficient for predictive purposes. In fact, we need to have this kind of flexibility that tracks the variability within the windows of interest. Now, the problem in what I present here is that such a model I can fit within a 10-minute horizon, which is the typical amount of windows within which we gather also our SCADA information on the mean wind speed and direction. But every time these would change, I would have a new coefficient structure. And that's why we have the second level where we express these autoregressive models as dependent models to these influencing agents. And once we do this, we are able to actually extract these data-driven indicators, which essentially were the difference between what we observe and what we measure. There's a training period used to do this. And then in a validation phase, we track this error, which of course is a statistical quantity that is bound to result to certain outliers. But in order for us to construct robust indicators, we also, in the second stage, need to pay attention to the persistence of these outliers, which means we have to conduct a probabilistic analysis, an analysis that can categorize or give us a labeling of these outliers as either instances where the operation of the system is as it should in a statistical sense, or instances where we're observing deviation from the proper response of the system, a deviation that is actually alarming and issues a red alarm, or instances within which the system is not behaving as it should, as expected, but in fact, we also have a range of influencing agents, such as, again, the temperature, in this case, or the orientation of the wind, which is outside of the regular bounds. In these cases, we're issuing an orange alarm, which notifies the operators and the owners of these wind energy sites that something is off, but it could possibly be because we have new and previously unobserved situation of the dynamics. So we have been developing these indicators, and we have been using this so-called drag system, red, amber, green alarm system, because this is something the engineers and the operators feel comfortable with. They prefer to have this over a continuous indicator that they cannot necessarily explain or assign some sort of confidence on. And we have even used this kind of a logic, not only for detecting whether a damage could be evolving in our system, but also for feasibly localizing this damage. And this is in fact possible even if we only have data available by looking at the distribution or exploiting the distribution of the sensors on the system. So often we also place the sensors in a way that is indicative of possible expected damages. We have verified this concept on another type of structure. This is a bridge structure on which we employed a network of sensors. We also controllably damaged this bridge structure until failure. This was an experiment that we used as a benchmark, and we showed that it is possible to use data-driven information from acceleration and strain sensors and understand also not only where or when the damage occurs, but even where is the location of this damage if we look at the axis along our bridge structure. This, to some degree, is feasible, and it essentially refers to the tasks of diagnosing damage, meaning understanding if it's there, and if it is, where could it possibly be located at, even feasibly, if we have monotonic indicators, what is the quantity or the extent of this damage. But it is not very helpful for the very important task of prognosis, which I mentioned before is the culmination of the tasks that we have to do in structural health monitoring. In the task of prognosis, we have to be able to say how much longer the structure can take or prognose, in a sense, what is its remaining life. And the only way in which we can do this is to accept that data is not always enough, particularly for these kinds of tasks. So purely data-driven representations, as I tried to argue before, are already shown to be very robust in different domains and applications for diagnostic tasks, understanding what is there, but they're not very good at extrapolating, at understanding what is the future life of a system or a component for unseen or previously unexperienced loading conditions or environments. And here is where a physics-based representation can help us do more, can help us go beyond data alone. And this is essentially the task that we want to, that I want to here present in what is called a hybrid approach to modeling. Hybrid models try to merge the best of both worlds, bringing data and physics together into a unified framework that can be used for paths such as digital twinning, predicting the response of the system, understanding its useful and remaining life under unseen loads. And in order to do and accomplish these tasks, usually we need to also have very efficient physics models, because for the variety of, or not the majority, but at least for several of these tasks, we would like to be able to do these predictions in real time so that we can have an interaction between the physical and the digital twin component of our system. So I will try to here present different frameworks that try to achieve such a balance where the physics can be reduced to the point where it can be used on the fly as data is attained. Focusing on this, and before I show you this real-time kind of concept, I also wanted to show you some projects that we work on where we're exploiting physics, but in a more offline manner. And a good example for such a project is our AeroSense project. This is a project where we're developing a new type of sensor that can be thought of as a sleeve that is wrapped around the blade of a wind turbine. And it gives distributed pressure measurements around the location, the airfoil where it is being wrapped. And this can be also, we can imagine the sleeve as also being wrapped around more than one locations on the blade. Now, this is a new type of sensor, and we wanted to use it for understanding whether we can predict erosion effects for blades. In this case, because data is not yet gathered at bulk, as this is a relatively young system, we had to resort to simulation for understanding if this is possible and understanding what kind of indicators or frameworks we need to use with the eventual gathered data. So we did so. We tried to simulate the expected response of such a blade. We tried to also simulate probabilistically the effect of erosion. And we showed that if we indeed have these pressure measurements, we can use a transformer model, which is a type of time series model, but in the deep learning actually sense, that can extract or follow the characteristics of the dynamics of response of such a blade, and on the basis of which we can create different types of data-driven indicators whose classification at the end can give us a monotonic effect, so an effect that shows us erosion at different scales as this evolves. So this was an offline sort of exploitation of the physics, not in the interacting sense, but very valuable for us for understanding and validating the potency of the monitoring system that we have developed and we're now actually testing. In the same project, we're using physics in a slightly different way to see if we can extend the predictive capabilities of these pressure sensors to not only pick up what's going on at the sensed location, which is of course the airfoil boundary, but also in understanding whether we can extrapolate these readings to get some more information on the flow that surrounds the blade. And if we can do so, we would like to then use this for understanding the wind distribution throughout the farm by monitoring different blades within a farm. Now here, in order to achieve such a task, we try to exploit the logic of graph neural networks, which in a sense give us a way to replace numerical meshes. This is the way in which we view them as an alternative, a deep learning, I guess, alternative to this. And we showed that we can indeed create such a graph neural network where when the information on the grid nodes, the airfoil is observed, we can get a prediction of what you see here, the flow around this section. So here you see the ground truth versus the predicted values for different configurations of the steady state flow. It's not yet a dynamic simulation, but you see that we're not doing too bad. It's a good approximation. It's not perfect, and we're aiming to improve this, but it means that we can use such a sensor, such a pressure-based sensor, and see if we can extrapolate to the prediction of the flow beyond the location where we measure. Now, in all of these configurations, what I showed you was an exploitation of physics that was done in a purely offline manner. There was no real-time interaction. But the truth is that for us in condition monitoring, the real-time interaction is highly important for a number of tasks, including, of course, digital twinning, the so-called task of virtual sensing, which basically is the task of inferring information of the response or measurements, artificial, let's call them measurements of a system in locations that actually do not have sensors. This is very important because it means that we do not have to use a very dense suite of sensors on a monitored system, which is always, of course, a bottleneck. We cannot promise to very densely deploy sensing instruments and networks. We would like to keep this always at a minimum for also satisfying some sort of cost to benefit ratio. And so using this kind of real-time predictive virtual sensing schemes, we can achieve predictive tasks that can be fused with diagnostics, prognostics, but also control, using minimal cost and effort. Of course, the effort comes from the domain of modeling, where we have to compensate for what we lack. And we have to do this also for effects that can be non-trivial, such as, for example, nonlinear dynamics effects that are often underlying operating systems, the effect of the influences from the environment that I referred to before, the fact that our loads, which are, by the way, never easily measurable, you cannot promise to very precisely measure a wind distribution along an excited system, the traffic that crosses a bridge, the wind that is loading a bridge, and so forth. So our loads are not precisely measured, and they're also distributed most of the time. And our measurements that I mentioned before are usually sparse. They're also corrupted by noise. Most sensors have to deal with the fact that we do not have perfect instruments. We have some sort of disturbance or noise levels that we have to deal with in our simulation. And we also have to deal with the fact that our systems are usually large. And so their computation, if we treat them using a very precise engineered model, could necessitate hours or even days. And this is simply unacceptable if you want to do real-time computing. So how can hybrid models be exploited? We would like to bring computation down to the point where we can actually do hybrid simulation experiments. This is something we do often for testing critical components of a system. Here we have numerical models that are computed very fast and which are interacting through actuation and control with pieces of the real system that are volatile, such as, for example, joints of particular characteristics that we wish to test, and where we have to achieve this real-time synergy between the models and the physical specimen for applications in control, but also applications in real-time prediction, such as, for example, in seismic monitoring. We would like to be able to predict fast enough to be able to issue alarms, to issue tags and labels about the condition of the monitored buildings shortly after an earthquake. For all of these tasks, we need hybrid models that can compute in real time. And so I will explain here our logic, at least what we try to follow in our group for developing such models. Here is the premise, or let's say the context of such an example. We assume we have some sort of monitored system. You can imagine that this can be, for example, the blade of a turbine or the wing of an aircraft, where typically we could have sensors that are deployed on such a system, either, as I mentioned before, accelerations or strains is a very typical quantity that we like to measure because it is indicative of condition. But of course, these are fine. It's a finite amount of sensors, and we would like to be able to extract the response of the system in feasibly also unmeasured locations, ideally as many locations as a model would predict, in order to be able to judge what is the condition of the system and if there is potential damage based on what it is that we predict. And so we have to fuse sparse measurements, usually with the model of the system, because as engineers, we are in the capacity of fashioning such models, and we would like to do this in real time. And the framework that we use for this in my group, and we have been developing for years, is Bayesian filtering. And I'll try to explain in a nutshell how this operates. So assuming we have a structural system or an engineered system at large, where we have a few sensors that are monitoring the response of the system at select locations, and where the system, as I mentioned before, has distributed loads where most of the time we do not directly measure these loads, these excitations of the system, but we do have a model of the system that could be rough and approximate, nonetheless exists more or less as a structure. So the model itself is there, but is uncertain, as expressed through its parametric configuration, which is not necessarily known. We would like to have an instrument that fuses everything together and predicts the response of the system in unmeasured locations for downstream tasks that are meaningful for engineering, such as, for example, strain estimates in unknown, unmeasured locations, which are useful for fatigue estimation, for example. It's one of the indicators that is necessary for residual remaining useful life prediction. The challenges that we have to work with for making this task happen is, first of all, the uncertainty in the data and the model that I explained before, the fact that the model could be complex, so beyond the usual assumption of simplified linear systems, the fact that our observations are noisy and limited, and the fact that the system can be large. So I would like to explain what we do for the case where the system is large. Now, traditionally in our group, because we are a structural mechanics group, we have been developing all sorts of methods for simulating fracture, hysteresis, nonlinear material nonlinearity, such as plasticity effects, or geometric nonlinearity, such as large deformations, or even responsive systems that are large assemblies of several components. All of these methods have traditionally been there. The issue is that they are never quite making it at the critical milestone of performing in real time. So what we do is we take these, to the degree feasible, accelerated simulations, and we try to boost them even further. A way to boost them even further for deriving real-time surrogates is to use a machine learning approach, for example. In this case, I present one alternative, which relies on exploitation of numerical simulations in an offline setting. So we assume the engineering model is there, and we try to recreate the response of this model in all of the degrees of freedom, in all of the locations of the structure that are of interest. And we use these responses for training an autoencoder, essentially a neural network that has two phases: the encoder phase, which tries to bring down the large dimensionality of the system to few latent variables that are still indicative of the dynamics, that are capturing the silent dynamics effects. And what we do is we try to then, because we describe a dynamics phenomenon, we use this lower dimensional space, and we try to develop essentially a time series model, an autoregressive type of model, which is now delivered through an LSTM, a bit dissimilar to what I showed before, but very similar in logic, where we now have the dependence of the force we're inputting into the system with this lower dimensional representation. This is propagated in time, and we can actually simulate the whole dynamic response of a quite complex system, although this takes place in these reduced non-physical variables. Now, the very good thing about the autoencoder is that you always have the decoder step, which can be used at any time step of the simulation to take us back to the original coordinate space. And this is key for us in monitoring, because the variables that we are actually tracking, monitoring, are physical variables. So we need to have a way to return to this full order representation and connect it to the data that we receive. So this tool here is something that we have used in different forms. We have actually shown its performance on a nonlinear benchmark that we have developed for the community of nonlinear dynamics, using a frame with the different hysteretic nodes. So this is a multi-nonlinearity type of problem, where we use this autoencoder logic to bring the computation down to real time. So a simulation that takes place in fragments, actually, of the actual computational time, so that then we can combine this framework with data, which is something I will show next. Now, there are a few details here for those interested particularly in the problem of dynamics, such as, for example, the fact that we use primarily a variational autoencoder type of network. And the reason why we do this is because we showed that for a nonlinear dynamics problem, the imposition of a latent space that is that features uncorrelated variables implies that we're actually approximating what is called the nonlinear set of normal modes. And for us, this is particularly important because it means that through this kind of deep learning surrogate, we are approximating the nonlinear normal modes of a system, which means that if we look at the spectral analysis of these decoupled latent features, they seem to be dominated by single frequencies. Now, this is important because then it means we have also decorrelated the main ways in which this nonlinear system can deform, and then we can better localize and understand damage. This wouldn't be feasible with more naive latent space representations, such as, for example, PCA or something that is traditionally used in a black box sense. We developed, we have demonstrated this through simple experiments, but more recently we have been collaborating with Siemens Gamesa for the problem that for us started it all, which was the nonlinear response of monopile systems. These wind turbines are usually fixed in soil through monopile foundation. The soil foundation connection is actually a nonlinear connection that can be described as these nonlinear curves. And where it is imperative to try and develop something that is accurate enough to predict the response, but also compute fast. So we took the previous framework that I explained, and we have now implemented this on these wind turbine simulations. And in the next level, we hope to now also use measurements from fiber optic cables that are installed in such monopile systems to see how well the predictive capabilities of such models can capture actual response that is observed on the field. Now, in what I showed in the previous slides, I have only not referred to the aspect of dependence on different parameters that could be governing the problem, but which is actually an issue that is often underlying our problem. So the dynamics of a system, as I mentioned also in the beginning, could be dependent on the characteristics of the load, but also on the characteristics of the system, how stiff it is, what is the damping that is present, and so forth. And the proper reduced order model should account for this parameterization. And a way to do this is to develop such models using the principle of projection, which means that we have some sort of dynamics equation in n, a high degree of freedoms, a high number of degrees of freedom, which we try to reformulate in a new lower dimensional equation, R, where the degrees of freedom are R much lower than n. The logic that can be exploited is essentially a Galerkin projection, but all it means is that we have an original reference model. We run several simulations, which we call snapshots from this model. And from a singular value decomposition, essentially, we extract a matrix that can be used to pre-multiply and pre- and post-multiply the components of this equation to bring it into this reduced space. And this can also be done also for nonlinear systems, which is really helpful for us. However, the dependence on these parameters has also to be done or expressed in a very in a convenient manner, a manner which does not violate the properties of orthogonality, for example, that we need to hold for these Galerkin type of projections. So there's many ways to play with the construction of these surrogate models, and we have also suggested a number of fixes for optimally constructing such parametric dependencies in a computationally efficient way. I will not stick to this because it's a bit beyond the scope of this presentation. Instead, I will go directly to the part where I think the interest is higher, which is how do we combine these models, which I showed you can be reduced, with data. So the principle is the following. We now have these fast to compute dynamic models. Either they came from one or the other approach that I showed for reduction. This boils down to some sort of equation of a system that could be nonlinear. And we also have some sparse measurements from a dynamic system. And the way in which I would like to fuse both is through this Bayesian framework that I explained in the beginning. And all this Bayesian framework boils down to is essentially these two steps. First, the step of prediction, where we assume that we use or we rely on the model equations, the reduced order model, for example, to understand the response of a system at the next point in time or throughout the dynamic simulation. And secondly, an update step, which is the step where the knowledge of the measurements comes in, and where we check the discrepancy between what we observe and what we predict, and we use it to correct our predictions. This is all there is to this principle. And when dealing with nonlinear systems, it turns out that it is necessary to also try to use some schemes that can flexibly account for nonlinearity. In our group, we rely quite heavily on the use of unscented and particle filters for achieving this task, which means that we account or we represent the dynamics at every point in time as a stochastic variable that can be Gaussian or not. It depends on the filter that we're using, but can be approximated by these sampling points. This is the behavior at the point tk. We use the model of the system, which is reduced and computes in real time to go to the prediction in the next time step. This gives us a new distribution of these points. And then we use these measurements, which we have from the system at sparse locations, the update step, where we correct this previous distribution to comply with the observations that we have in the field. This is the principle roughly described. Here I will show you an example of doing this inspired by one of our projects on aerospace systems, the SIMA-Aero project. Here we tried to explore the potential of virtual sensing and damage detection for fuselage panels of aircraft structures. These are very thin shell structures where we assume we have some sparse sensors of strain or acceleration, and we try to do two tasks. First, to predict the response in unmeasured locations, here represented with the green points, and secondly, try to infer the location of possible flaws on the system that usually in these systems would appear in the form of cracks. So we're trying to find the location, possibly orientation of such cracks. This is a parameterized problem because the flow is parameterized. We have different lengths and locations of this possible damage. And so we have a reference model of this fuselage structure that we try to build in a parametric sense, as I mentioned before, but in a reduced sense as well, so that it can compute in real time. There are a number of numerical manipulations that we have to do to achieve these tasks for curved and thin geometries that include a crack. And for those that are interested, I can actually refer to these stages that are heavily relying on the concept of mesh morphing later on in the question section. But the important result is that we can simulate the dynamic response of this very thin structure, and including a possible crack of specific characteristics, and we can do it in real time. And if I can do it in real time, it means I can use the Bayesian framework that I showed you before, which runs these Bayesian filters that I referenced before. So different model configurations for different candidate sets of parameters, which are updated. They are run parallelly as banks of filters that allows us at the same time to do two tasks. First of all, understand what is the best candidate configuration for a crack to exist, which means I can localize the possible flaws on the system. Here you see the convergence as the evaluation takes place towards the correct, the actual reference crack for the simulated example. And quite importantly for us, we can also predict the response of the system in locations other than the ones we measure, which is what you see here in this time history recovery plot. And we can do this at fragments of the time that would be required to do an evaluation of classical finite element models. In this yet simple still example, for instance, you will need 71 seconds for this estimation, maybe 22 with certain tricks for reducing computation. But it takes only 0.12 seconds to do this estimation using our reduced order model. And this is very valuable for the parallel computations that we're conducting. Now, in what I showed you, I stuck to some simple examples. And so I'm now going towards the end of what I would like to discuss as the final issue of complexity. And here is the issue of how do we deal with systems where, okay, we can construct a model and maybe it is uncertain, but further to what I showed before, it's not only an uncertainty in the parameters of the model, but there's possibly an uncertainty in elements of the model that are not appropriately accounted for, such as nonlinear terms that we did not know existed, such as damping effects and hysteretic phenomena that we never appropriately accounted for, and which we find are actually characterizing most of our operating systems. What do we do in this case? Well, in this case, we would like to have, again, a Bayesian type of framework that operates in two stages, as I showed before, a prediction stage and an update stage where we correct for what we observe, but we want to do it in a more loose way. So here we're using deep learning structures to infer these Bayesian filters that I explained earlier. A first approach that we have suggested for doing so is what we call the physics-guided deep Markov model, and I will explain a bit on this in a few. But we have also suggested frameworks that draw from the extended Kalman filter form for those that are comfortable with these filters, or also frameworks that are instilling Hamiltonian principles in our prediction framework. Now, for most of these frameworks, let me just go straight here, we are relying on the concept of the so-called deep Markov model. And this is a model that tries to replace the functions that I showed earlier of a model just with a black box, a deep learning framework. But for us, this is not very useful. So as always, we try to bring in the physics in there. So we modified the original configuration of a deep Markov model by adding a physics-guided model in the loop, which forces our transition equations to maintain a physics-based character, even if we're not fusing the complete physics, because this is the problem in this case. There is an aspect of the physics that is unknown, and that aspect is taken on by a learning representation, a neural network that accounts for the discrepancy between what we know and what is really there on the actual observed system. By doing this reconfiguration, we can tackle a number of different problems, including, for example, the onboard monitoring problem that I mentioned before. Here, we have some models of the vehicles, but they are not perfect. So we fuse some of the knowledge we have on these vehicles. And by doing so, we're extracting a better approximation of, for example, the estimation of the roughness of the road pavement, which is traversed by these vehicles. I'm showing you here. Let's see if the video will load. Oh, sorry, it was too heavy. Let me try again. Let me avoid the video just so that we don't have the same issue. And I'll show you another example for doing so. So let me show you this. Sorry, I'm dealing with the controls of Zoom, but hopefully now you should see the full screen. So here I'm showing you the example of a pendulum system. It's a nonlinear dynamic system where the observations that we have from the system are in the form of images from a video. And here's the principle of what I tried to explain before. We fuse a physics-guided model, which is just an approximation of the real nonlinear system. Here it's a linearized equation. This is how we force the latent space to evolve. And what we're observing is actually just video data. So we don't have a perfect idea of how this connects to the latent space, of course, but this is recovered by the deep neural network. All we ask for it is because we're dealing with images, we just specify that it is a Bernoulli type of distribution that has to be used. And when we do this, we see that we improve the inference of the response of this system. We can very well approximate both the angle and the angular velocity, which is not something that can be achieved by a pure black box approach, an approach that never saw this partial fusion of physics. And the reason why this is the case is because in this case, we can only predict more or less what we observe. We cannot infer physics-based variables like the velocity, which is the derivative of the displacement, because this information is just not there for the deep Markov model. We're exploiting these principles for a number of downstream tasks that are relevant for structural health monitoring. But because I have exceeded my time, let me not show you this, but just take you to the end, the desirable result, which is to extract these kinds of indicators of the condition of the system, to attach a probabilistic and uncertainty quantification onto these indicators, how certain we are about these, and try to map, therefore, the indicator to an associated action that we need to take onto a system. If it is a bridge, what is the optimal action that we need to take to correct a suspected damage? And also, what is the optimal next observation we should take from the system so that we can have an improved estimate about the new and updated condition? And by using this framework, we try to develop a policy planning for engineers and operators that can give them an optimal type of organizing their action within a prescribed horizon. The strength that is offered, that we have to do this, is the use of this combined use of data and models, which is the principle of the value of information. We also have some implementation of this, for example, on railway infrastructure systems, so on actual monitored systems with data that we derive from onboard vehicles. This is the type of policy that we discuss. So at every time of a decision horizon, how do we advise the operators to take a suitable action onto the system? And we try to base this logic onto what we call the value of information or the value of structural health monitoring, essentially the confidence that we can attribute on our indicators and on our predictive capabilities. With this, I would like to close. I would like to close with this slide, which expresses this vision to go from data to more robust documentation through physics in the loop, through offering of these indicators for the purpose of decision support, and trying to do this not for individual entities, but for actual populations of systems, which reflects an augmented type of approach to digital twinning. I would like to close with this slide, which is more of a vision slide, and take any questions. Thank you very much.
Thank you for that lovely presentation. If there are any questions, please can people raise their hands? Vangeli, please go ahead.
Yeah, thank you very much, Eleni. It was really exciting how many different things you are doing there. I mean, I was aware for a few of these works, but not all of them. So it's really amazing.
The reason why I struggle is because I would always like to show the full chain and the logic in which we go from one step to the next.
It's very interesting. Just a couple of, let's say, more specific questions or a bit about the model. So, yes. For example, you mentioned about this model order, the reduction.
Let me stop the share so I can see you.
No, I think it's okay. I think actually in one slide, I think it was slide 33.
Okay, maybe I can bring it up. Yeah,
if it is easy for you. I was just wondering, how you choose, let's say, the functional form of these models, and whether you need to prescribe the dimensionality of the underlying, the low dimensionality space, let's say.
Which is the slide you were referring to?
I think it was this parametric model order reduction, slide 33.
Okay. Yeah, let me go there. Yes, the projection-based reduction logic, right? Yes.
Yeah, because this is something that it's. I mean, we use it also quite often in this.
Yes, of course. I think it's quite either a proper orthogonal decomposition or proper generalized decomposition. There are many different ways to do this. What I show here is, of course, the proper orthogonal decomposition.
Yeah,
and you will notice
projection operator format.
Exactly. Now, of course, this kind of projection is linearized, but you have to think of the following. It's linearized in terms of the parametric space. The fact that I here still retain, let me try to use my pointer, that here I still retain this nonlinear term is what gives me the strength to still approximate nonlinear systems. Just to mention this, because often there's a confusion between what is a projection, what is the linear and the nonlinear.
Yeah. So do you need to prescribe to give these functions J? That's my question.
Yes, so this is the yes and no. In the traditional scheme, we have a full order model that has a very specific form for this function G. And what happens when you produce these snapshots and you have the SVD and you extract the projection matrix is that you pre-multiply basically also this function G so that you can reduce it, bring it into a reduced form. So it has a prescribed form. It has a transformed formulation which can be computed in reduced dimensions. It is actually even further reduced because we use hyperreduction. This is a very specific operation that allows us to compute this function at only a few degrees of freedom and not all of the degrees of freedom of a system. But it is also possible, and we have done some work on this with colleagues, to completely replace this function with a learned function, a neural network, for instance. We just don't want to do this if we're allowed to. We prefer not to do this because we prefer to have the physical connotation of G when this is useful. And in many cases, it is useful for us to bias the prediction with some sort of known model. In some instances, this is not enough. So as I showed before, you have to use something learned to compensate for what the physics doesn't know.
And what is the dimensionality of the low dimensionality here space is K?
Here, the low dimensionality is here, in this case, is R. And the higher is R,
And do you need also to give R, let's say, in advance, or is there a way to be automatic?
No, so usually we follow the logic, what we do also in autoregressive models, where we try different orders. And we try to use, for example, a Bayesian information criterion. Then we select the order that makes the most sense in terms of parsimony. So we don't have a very loaded, we have a model where It's not over parameterized, and where you can avoid phenomena such as overfitting, for example, but still can capture most of the important information.
Okay,
So
thanks,
it's not
Eleni.
fixed. Normally,
Yeah,
you
yeah.
should try to select it doing some sort of parametric analysis.
Okay. And another one, if I may, just a bit more general, let's say, I mean, it's very interesting, always coupling between the hybrid, let's say, physics-based and data-driven, which of course, as you say, is the modern trend now, and it's extremely important. I'm just wondering, is there any way in your system, in your applications, to quantify the uncertainty, let's say, introduced by the different approaches? So use, let's say, standard UQ-based schemes.
Yes, unfortunately, I don't have it in the slides here, but I can send you this information. It's a shame, actually, that I don't have it, because specifically using this kind of a framework, for instance, we show that if you construct this reduced, this reduced matrix, I don't show here the details, but it's basically linked to the dependence of your basically the dependence of your nonlinear model on this parameter space, right? Now, of course, this comes with some uncertainty. And one way to account for it is in the derivation of this reduced space to use, for instance, a variational autoencoder logic. What does the variational autoencoder do? It gives an extra set of reduction complete with a probabilistic definition of the latent space, dependent on, because we use a conditional variational autoencoder, we can also condition it on the parameters. And then when we generate, because sometimes we use this as a generative model, we do this by sampling through the latent representation and the conditioning of the parameters. So it's really a very nice tool for giving uncertainty quantification bounds also on the estimate.
I was thinking also that you can use Bayesian approaches, where you have, of course, the full distribution.
Of course, also this, or if you have data, right? You can have the logic that I showed you. This logic gives you also a covariance matrix of the estimate. It's not a deterministic, which is the very nice thing for us. There's also the confidence interval surrounding the prediction.
Thank you very much, Eleni. Excellent.
No, thank you for the really on point question.
More questions?
I have one question. You said that sometimes you will discover some phenomena that is you didn't know it's there for, and you show the rates.
Yes.
How often is?
It's a good question. So it depends on the system that we monitor. So in structural engineering, sometimes we can get away with models that are not too far from reality, which is a good thing for us. This is usually the case for systems like bridges, for example, when they're operating under normal, regular, and expected loads. The issue is if you have, for example, earthquake, or if you have a phenomenon that excites geometric nonlinearity, when things start becoming a bit more nonlinear, it's not guaranteed that we have a very good approximation of the nonlinearity that is taking place. And what's even worse, usually, is to account for the actual damping that is in place, because our assumption on damping, which is usually a Rayleigh type of assumption, is a convention. It's not guaranteed to actually reflect what's going on in reality. So in those cases, we usually have some sort of term that could be missing from what we suspect from the actual model. And that's where we found useful to include such a term that is learned. Others have done the same by using Gaussian processes. So they have a superposition of a model they think exists on the system, plus a Gaussian process model that approximates the discrepancy between the model and what is observed. This is not that dissimilar, but it's more convenient for us because it's for use in a real-time setting, because it's always, that's why you see here the time instant. This is always as part of an interactive dynamic estimation, real-time type of estimation that's going on.
Okay. Yeah.
Maybe to show you here, for example, I show this, this case is more of a simulated case, but also for real data. That's why we prepared it like this. We have this issue. We have here a car, and we would like to infer the roughness profile, which is sort of an input to the model of the car, to the dynamics of the car. And so the issue is we can never really have a very proper model of this car. It's always a simplified half-car model. The suspension maybe is not very accurately described. The damping mechanism that's there is not great. So, there is this initial model that at least brings our latent space estimation in physical coordinates, which is very nice for us, plus something we probably do not know that tries to be compromised so that we can get a best approximation of this roughness profile, which for us is a condition of the pavement, of the road, essentially surface in this case.
One more question, which industries they show more interest to put sensors and measure?
Yes,
The wind
it's a very good question because we have to deal with that, of course. So that if I have to place them in order, I would say that the aerospace industry is ahead of the wind energy and energy industry, onshore and offshore turbines. And the conventional structural engineering is the very last, is very slow in adopting these paradigms, although now many new and bigger important works like very big bridges are being instrumented, important dams are being instrumented, but they're very slow to uptake this concept of sensors. It is something, though, that now becomes a bit more common. I'm also myself participating in a number of different guidelines that are now emerging about instrumentation, about monitoring of a large civil structure. So I expect this to be something that is also soon evolving. In wind energy, it's a must, of course. The problem is that they have had for years a very specific protocol of what sensors they use. So they're very reluctant to add more, more sensors on the blade or the tower, because typically they have more or less most of their sensors and control systems on the nacelle, actually the top of the turbine, and they would like to avoid adding more things because it means their protocols have to be changed. So there we have to more or less deal with this kind of a reluctance. In the aerospace industry, at least the works that come out take as a premise that we can imagine new systems that could have new outfitted sensors or embedded sensors. I think it might be a bit more open, although, to be honest, because I myself, I'm not so close to the application. I think there as well some issues with the certification, and of course, uptake should exist. But I would order them in this respect if I have to. I think there is a raised hand. If I see it.
Hi, Eleni. Thank you so much. It was an amazing research and so many things that you have done. I've got a couple of questions.
Mm-hmm.
Just wondering. So, first question is about possibly dynamic structure of data. It might be the case that during sensing you might have to deal with some of the sensors failing,
malfunctioning. Yes, of course.
And then, how do you deal with that? Because you build I don't know if this is something relevant, but have you built kind of models to account for this? That possibly
yes. No, it's a very good question. Practically, this is also something we have to account for. So we have, in different works that I did not include here, also shown how to develop indicators of malfunctioning of sensors so that you can maybe take them out of the estimation part, because of course it will affect the prediction, as you say. And we also, in the indicators that we developed, I showed in the beginning, we had that yellow or orange alarm for the case where the system is experiencing a situation that seems new. In that case, the environment of the sensors themselves is basically part of that condition indicator on the robustness. So if something odd is observed with respect to the sensors themselves, it would add to that statistic and would try to issue an alarm that prohibits us from using the prediction as it should. There are different schemes, but what I can say is that it's always good to design a sensor distribution that is to some degree redundant. It's not only good for the case or the instance where there might be some malfunctioning of the sensor. In fact, we also show that you can use this redundancy to infer an uncertainty quantification framework on the confidence of its sensor. How can you do that? You can adopt a leave one or leave k out sensors in the prediction, which gives you a way to actually also, through this redundant sensor that you keep as a test, you can quantify the level or the precision of your predictive capabilities by doing something like this. And you can use this logic also to get rid of a sensor when it's actually malfunctioning, in fact. But it is an important issue. There's actually colleagues of mine that have quite important work exclusively on this theme. So how to deal with sensor malfunction, for example, but exactly because it is something we need to guarantee for the actual practical use and application of these frameworks.
And my second question is whether you might have cases where microscopic phenomena become so important that that you need to account for them.
Yes.
Because I can see the finite element methods at some point
Are macroscopic, of course, exactly as you stated. And specifically, for instance, as you may suspect, for the crack detection issue, the crack itself is nucleating at a micro scale. So there's two frameworks in which monitoring can be exploited. In some cases, for example, in practical applications like concrete bridges, it might not be important to detect the crack at a very early stage because there's multiple micro cracks. It might be more important to understand when it becomes threatening to the system, and that's okay. In that case, maybe we can use macroscopic methods, as I showed, to try and deduce this. But in case where we're actually more interested in capturing the crack during its growth, and even at an earlier stage, then the appropriate type of monitoring should also change. It should not be a vibration-based monitoring of accelerations or strains that are dynamic, but more of a monitoring that relies on the propagation of waves. So we have a separate, let's say, a separate tool that we use in that case. It's more called non-destructive evaluation, and it's basically a guided wave-based approach for understanding the nucleation and growth of smaller flaws like cracks. And in that case, we're using higher frequency ranges. We use repetitive pulses that are propagated through a medium, and we try to also use a network of sensors that are receivers of those waves, and where the analysis then becomes an analysis of a wave propagation phenomenon, less so an analysis of model or vibration, let's say. So my point is not only the method, but even the tool, the monitoring tool has to change when you're interested in such phenomena.
Okay, I'm done with my questions. I have some of that other things I would like to discuss, but we usually have the more informal discussion after we finish.
Yes, I wanted to mention for everyone, of course, because this is a virtual seminar, but it would be great. I don't know if I have I realize I don't have my email on the slides, but I would like to just urge you to simply email me if you have any follow-up, because for us it's an opportunity to create new research potentially out of this such an interest. So please contact us, contact me with any questions, and I will also share the slides for this purpose as maybe an inspiration to possible questions.
For us as well, Eleni. So I think in any case, it would be nice, especially if you share, as you said, the slides.
I will,
to digest a bit all the information, and then we can consider,
That's why I wanted to do this tomorrow. If you allow me, I will also add some links to the relevant papers just for more information on each example. I think then it's a bit more.
But first, let's see if are there any more questions from the audience before. I mean, in any case, I think we should stop recording. But if there are more questions to Eleni, please.